EDX Corpio, Vectors 2, Equations of Lines, the equation of a line in 3D in Cartesian form. Sometimes a vector equation may be given in Cartesian form, as we can see here. The first equation is a Cartesian form of a 2D line, and the second equation is the Cartesian form of a 3D line. And I think you'll often find it easier to convert these back into a vector form in order to tackle a particular question. So if we want to convert the vector equation of a given line into the form ax plus by plus c, then we take the given vector equation. So here we've got r equals the vector 1 minus 3 plus lambda 2 5. And one way of tackling this problem is to pick out the x component. So the x component of r, so x is going to be 1 plus 2 lambda, and the y component of r is going to be minus 3 plus 5 lambda. If you rearrange each of these for the parametric value lambda, so there's lambda in terms of x, and then we've rearranged to get lambda in terms of y, and we know they both equate to the same value of lambda. Lambda can't change in the middle of the middle of a coordinate, if you like. So we get that x minus 1 over 2 equals y plus 3 over 5, and they are both equivalent to lambda. And by rearranging this, we can get to 5x minus 2y equals 11. It's worth noting that if we rearrange this for the gradient, we would get m equals 5 over 2, which you could see in this direction vector. The gradient of this two-dimensional line would be 5 over 2. So in 3 dimensions, we've got r equals a plus lambda d. You can see it's been represented by a 3-dimensional vector. So the position vector, given position vector is a1, a2, a3, and the given direction vectors d1, d2, d3. And if we consider r as being x, y, z, so the top line is x equals a1 plus lambda d1, middle line y equals a2 plus lambda d2, and similarly z equals a3 plus lambda d3. If we rearrange each of these for lambda, so for example in the first one, lambda would be x minus a1 over d1, and we do the same for y and z, we end up with x minus a1 over d1 equals y minus a2 over d2 equals z minus a3 over d3, all of which equal lambda. And it will be worth considering and thinking about what would happen if any of the components of the direction, for example d1 or d2 or d3, were 0. And that's something you can look up on integral or in any textbook on vectors. So it's something for you to think about. So if we want to go from vector to Cartesian form, so here we've got a vector form of the line, and we know that x, y, z is the equivalent of r, the general point on the line, and we pick out the x component. We've got x equals 2 plus lambda, middle component y equals 4 lambda, and the bottom component z equals minus 3 minus 2 lambda. And if we rearrange each of these for lambda, so lambda can be written as x minus 2, lambda can be written as y over 4, and here lambda can be written as z plus 3 over minus 2. So we can write this 3-dimensional line in Cartesian form as x minus 2. You can think of it as divide by 1 if that helps, although that's not essential, equals y over 4 equals z plus 3 over minus 2, and of course they all equal lambda. As we can see there. So in this problem we're going from the Cartesian to the vector form. So given the slightly awkward looking Cartesian form, and my advice generally would be to turn this into a vector form. So if we look at the first pairing, if you like, we've got x minus 1 over 2 is lambda. If you look at the second pairing, y plus 2 over minus 4 is lambda. And if you look at the last little equation, we've got z over 3 is lambda. If we now rearrange each of these for x, y and z, so rearranging the first one, we get x is 1 plus 2 lambda. Rearranging the second one, y is minus 2 minus 4 lambda. And rearranging the third one, z is 3 lambda. So we know that x, y, z represents our general point R. So we're looking for a position vector plus lambda times the direction vector. So the direction vector will be the coefficients of lambda. So the coefficients are 2, minus 4, 3. And the position vector would be, in the x case, would be the 1. In the y case, the minus 2. And in the z case, it would be a 0. And that is the more useful vector form of the line, as we can see there. So something for you to think about. If we were finding the equation of the line through 0, 2, minus 1 and 4, 1, 0, and we wanted the answer in Cartesian form. So if you want to pause the video at this point and think about that. And my advice would be to go for the vector form first. So get it into the form R equals position vector plus lambda times direction vector, and then convert that into the required Cartesian form. In the next session, we're going to be looking at the intersection of lines in 2 dimensions.